Now, the last thing I would like to mention here is another definition about groups, which is the order of the groups and the order of the element. What do we mean by that? Well, the order of a group G, star is simply the number of elements. Okay, and this can be written as n G between brackets or G with these vertical lines. Now, obviously, if G has an infinite number of elements, the order is also infinite. And guess what? If it's a finite group, it is finite. Well, that's deep. Then also elements of G can have an order, which is the smallest positive number m, which makes true that a to the power m, so which is not the result of a set of multiplications but a line of star operations, remember. Okay, and this a m times needs to give me the identity element e, and the order is then the number of a's I need to use to reach that. Now, to give you a little bit of feeling how you can work with this, I would like to show you an example. This example from page 147, example number 51, and I start with the set Z, and Z4 means I have the 4 first elements of Z being 0, 1, 2 and 3. Now what I want to have is this set but without the 0. So I take the 0 out and I end up with the set 1, 2 and 3. And the operation star, which is defined as a multiplication modulo 4. Okay, so let's have a look. Is this a group? Yes or no? That's the question. So I have a look at the Cayley table and see if it works. Cayley table is about the star operation. I have the elements 1, 2 and 3. And then, for instance, 1 star 1, well, star is here a multiplication, so to make that clear I can write it in a different way. Instead of star I can use the multiplication sign, and because it's modulo 4 I write there a 4. So what do? I do 1 times 1, which of course is 1, divided by 4, and then the remainder will be 1. 1 times 2 obviously is 2, divided by 2, the remainder will be 2, and here the remainder will be 3. Here the remainder will be 2. 2 times 2 gives me 4, divided by 4, that is obviously goes 1 time, and then the remainder will be 0, and here 2 times 3 is 6, the remainder will be 2. Then 3 times 1 is 3, remainder will be 3. 3 times 2 is 6, divided by 4 is 1 time, remainder 2, and 9 divided by 2 I have a remainder of 1, and that's my Cayley table. Now what I notice is that I have here the element 0, which means that this group and this set and this operation star or x4 are not closed, because one of the outcomes is 0, which is not an element of our set. So therefore it is not a group. Now the next and last example is example 55, and in this case I use the set Z4 in its entirety. So I have the elements 0, 1, 2 and 3. The star operation now is defined as plus 4 modulo 4, and I'll write it like this. And again, is the question, is it a group, and if so, is it an Abelian group? So let's have a look. Again, I am going to look at the Cayley table. I have my elements. No, 0. 0 plus 0 equals 0, so the remainder is 0. Here the remainder is 1, 2 and 3. Here the remainder is 1, 2, 3 and 0, etc. So 2, 3, 1, no, 0, because 2 plus 2 equals 4. So divided by 4, it gives me a remainder 0, and here 1, and here the remainders are 3, 0, 1 and 2. Now what I see here, that the first axioma is in order, because I see that this structure is indeed closed. So that is dealt with. Then the second axioma was the associative law. For instance, is for instance 0 plus 1 plus 4 plus 1 plus 4 3, where I first calculate this, equal, for instance, to 0 plus 4, 1 plus, and this is 3 plus 4, where I calculate first those. Now let's have a look. If I do 0 plus 1, that's obviously 1, and divided by 4 gives me a remainder 1, plus 4, 3, which is 4, and the remainder will be 0. And here I have 0 plus 4. Now 1 plus 3 is 4, divided by 4 gives me a remainder 0, and I see indeed it is true. Now this is true for every combination, because I can use the fact that the associative law is true in Z. So therefore it's also true in a subset of Z. Then the next axioma was identity. Now does this operation star has an identity element? And obviously the answer is yes, because the identity element is simply 0. And the last element or idea which I need to prove is the fact that this star has an inverse operation, yes or no. Take for instance the operation plus 4, 1. Which brings me, for instance, from 2 plus 4, 1 gives me then 3. The inverse operation is then plus 4, 3, because 3 plus 4, 3 gives me 2. And the operation plus 4, 0 and plus 4, 2 are an inverse in themselves. So we can say that this group Z4 plus 4 is indeed a group. Now, is it also an Abelian group? The answer is yes, because within Z the commutative law is obeyed, and therefore it's also an Abelian group, which concludes my second screencast.